Hi, in this video we are going to uh, begin to discuss some of the ways that we can use the SVD to solve a number of very interesting and important problems. The first is application involving so-called low-rank approximations to a matrix. Most data matrices, most image matrices are either full row rank, or full column rank. That is, it is rare for there to be linear combinations or linear dependencies between the smaller of the dimensions of a matrix. And for matrices that have many rows and many columns, which includes both images and many sorts of data, this rank can be very, very large. This poses problems both for working with matrices, but also even just for storing them in a computer. Although these matrices are often very large rank, in a formal sense, they often can be very well approximated by matrices of much, much lower rank. What do we mean by that? We mean we start with a matrix, an m by n matrix, whose rank is the smaller of m and n. That's full row rank or full column rank. But we can find a matrix whose rank is much lower than both the number of rows and the number of columns, where this matrix is close to A in some sense. Why are these low-rank approximations useful? Well, in one sense, they can be thought of as a big picture view of a matrix. They capture the essential features of a matrix, but perhaps miss out on subtle details or noise in the matrix. This has a lot of applications, both in simplifying the storage requirements for a matrix, as we will see, but also in sort of intuitively understanding what it is that a matrix is doing. We focus on the big picture part of the matrix. How do we find a low rank approximation like this? Well, let's think about the view of a matrix as a sum of rank 1 matrices expressed in terms of the singular values. We saw that we can write a matrix A as of rank R as a sum of R terms, where each term is a scaling factor, a singular value, ranked in order from largest to smallest, multiplied by an outer product. This outer product UV transpose gives a matrix, a rank 1 matrix, where U, the set of U and the set of V are singular vectors, so they're orthonormal vectors. Right? That is, the U's are orthogonal to one another, the V's are orthogonal to one another, and all of them have a unit length. If we think about this, the set of UI and the set of VI are all orthonormal sets. That means that the magnitude of the entries of UI and the entries of VI will all be roughly similar. Their lengths are the same. They won't have particularly huge numbers, for example, which means this UI VI transpose, this outer product, will all give similar magnitude matrices that roughly look similar in terms of the magnitude of the values across all of these products. What does that mean? It means that what is going to dominate this sum, the effect of each contribution, is this scaling factor. This qualitative description here, this kind of hand-waving description of similarity of magnitude, can actually be reinforced and made stronger using ideas of matrix norms, but we're going to not worry about that at this point in time. Right? So if the primary effect, if what dictates the overall contribution of each of these terms to making up this original matrix is this scaling factor sigma I, this gives us a strategy to approximate A by simply taking the first K of these terms rather than all R of them. And we define this K rank approximation as this sum I equals 1 to K of exactly the same terms that we use to generate A perfectly if we were to take all of the terms. All right. In summation notation, we write it out in this. This can be translated into the matrix notation of the singular value decomposition as follows. Recall that the full singular value decomposition was represented as U sigma V transpose, where V could be broken up into a portion that described the row space, a orthonormal basis for the row space, and an orthonormal basis for the null space. And similarly, U broken up into an orthonormal basis for the column space and an orthonormal basis for the left null space. And sigma had this form, this block matrix form, where this is M by N, the same as size as A, where this sigma hat contains non-zero singular values, 1 through rank R, and the rest of the matrix is all filled up with zeros. For a full rank matrix, we might not actually have this zero block down here. Now, we can define a reduced rank SVD really simply by changing this sigma piece. What we want to do is we want to zero out portions of it. So what we'll do is we'll find out somewhere in here is sigma K, the last entry that we want to keep in our term. And what we will do is we will leave these sigmas exactly the same, and all of the ones that are beyond here, that are further down in the list, get replaced with zeros. You can write this as we're going to define a new sigma hat K that still has these R terms, but only the first K of them are non-zero, and the last ones, all of the ones beyond K, have been set equal to 0. And when we've done this, what this will have the effect of is zeroing out the corresponding entries in the product. U sigma KV transpose will give us exactly this sum. We can simplify this notation further by, rather than using this relationship to the original sigma matrix, to define a sigma K that is only a K by K matrix. And when we do that, we still have this sigma K is still M by N. But instead of being made, our original sigma had sigma hat 0, 0, 0, where sigma hat was an R by R matrix, which means that this remaining block was M minus R and this remaining block was N minus R. Instead, what we do is we replace with this with a k by k smaller non-zero piece and more zeros in this original matrix. Okay. And now we have something that looks very much like the singular value decomposition, simply with choosing the first k terms rather than all r of them. We are not going to prove this here, but it can be shown that this a hat k is not just a rank k approximation of k, but it is the best rank k approximation in a least squares sense of best. What does that mean? It means that if we take a look over all possible matrices, let's look at all matrices of the same size as A, but that are of rank k. We look over all rank k matrices, and we ask which one of those matrices has the smallest least squares error. That is, if we add up the difference between the matrix, an element in matrix A and an element in matrix X, and we square those and add all of those, which matrix has the smallest sum of squares error? It is this reduced rank approximation derived from the singular value decomposition. So not only does this give us a method to compute a rank k approximation, we have a definition of this as being a best approximation, for a certain definition of best, at least. Now, why are these reduced rank approximations helpful? Well, one is for intuitively helping to work with to understand what a matrix is doing. A lower rank matrix is smaller, easier to wrap our head around. And we'll see some applications of this in some upcoming slides. This also has applications to efficient storage, how we can store a matrix with less data than the original matrix had. This has applications, for example, in things like storing graphics images or large data sets. So again, let's think about our full matrix decomposition, full singular value decomposition, broken into row space and null space, column space and left null space. And when we multiply this out, we're going to find something quite interesting. Plugging in these expression for U and V transpose and our sigma matrix here, when we apply the block matrix sigma of sigma and V, we get sigma hat times VR transpose plus 0 times Vn. The 0 doesn't contribute. We only have this sigma hat VR transpose. For the second row, 0 times VR transpose plus 0 times Vn transpose gives us 0. When we then do the next multiplication, we get UC times sigma hat VR transpose plus ULN times 0, so that piece disappears. We end up with a product that only depends on the column space vectors, the row space vectors, and this sigma hat piece. We can ignore all of these 0 blocks. We can ignore the left null space. We can ignore the null space and still perfectly reconstruct A. This isn't an approximation. This is a perfect reconstruction of A, just ignoring the left and null, right null spaces. What this means is that we can actually store our rank R matrix rather as, instead of as a m by n matrix, we can store it as R vectors of length m, that's the columns of UC, R vectors of length n, the columns of VR, and the R singular values themselves. Right? The total amount we need to store is m times r for those UC vectors, n times r for the VR vectors, and r for the singular values. These all have an r that we can factor out. The rank multiplied by this m plus n plus 1. If we have a matrix that is low rank, that is, whose rank is much lower than the smallest of the two dimensions, then this product here will be smaller than m times n, and this will be an efficient way to store a low rank matrix. We can store a low rank matrix for much less in this sort of piecewise decomposition, for much less cost, for much less space than to store the original matrix m by n. However, if the rank r, if we have a full rank matrix, the rank equals r is equal to the smaller of m times n, then this storage cost is a little bit more than the cost of storing the original matrix. So let's say r was n. We would have an n times m piece, which is exactly the same here, plus an extra n squared and an extra n. So a larger storage cost. The SVD provides a way to efficiently store low rank matrices. It's not very helpful for storing full rank matrices exactly. However, we can take advantage of this idea to store the approximation to A in a very cheap way. We think about this reduced rank approximation, where we only have the first k terms of sigma, and we can break things down in a similar way. I'm now breaking things, rather than now being a set of vectors that describe the row space, they describe only the first k columns of the row space, and only the first k columns from the null space. And then we've taken the rest and we've put those extra pieces into this Vn. So we can sort of think of, we started with V row space Vn. We break this into Vk, Vr minus k, Vn. That is the first k pieces of the row space and the next pieces of the row space. And then, just for simplicity, call this Vk the first block and combine these two into not a real null space, not the null space of the original matrix, but the null space of this new matrix. Right? This is actually, this V hat k is the complete row space of A hat k. It's simply not the complete row space of our original matrix A. And we do the same thing for U. By exactly the same logic, we can express our low rank approximation A hat as a product of only these first k vectors of U, the first k vectors of V, and this scaling matrix K, which means we can store this as k vectors of length m, U hat, k vectors of length n, V hat, and our k singular values, k times m plus n plus 1, as the overall amount of information we need to store. Since we set this up as a low rank approximation, we know that K must be lower than the minimum of M and N, which means this is an efficient way to store data. All right. This is the idea of a low-rank approximation. Another application, building on the idea of a low-rank approximation, is the concept of principal component analysis. Principal component analysis is something that is specifically applied to data matrices. We can think of a data matrix as being corresponding to a bunch of different samples of different measurements, of different measured values. And so if we think about the case where, say, grade data, we have homework, we have exams, we have quizzes. And these are different measurable quantities. And for each of these, we can assess this with a student. Student 1, student 2, student 3. And in this structure, each column corresponds to all of the scores for one student. Each student is a sample in this case, and each column corresponds to all of the information we have about that one student. We might ask questions. Well, what are the most important factors in the class in terms of discriminating between students who are doing well, very well, somewhat well, and not so well, for example? Is it homework? Is it exams? Is it quizzes? Is it some combination of these? The way that we address this is by looking at the variance between these. We can define something called a covariance matrix. Don't worry so much about the details of this. The covariance matrix describes how much pairs of rows change in a correlated manner. That is, if the homework scores and the exam scores are correlated, it means that students that had high scores on homework also had high scores on exams. Students that had low scores on homework also had low scores on exams. That's a strong positive correlation. Negative correlation would be a case where the opposite was true. High scores on homework led to bad scores on exams, which would be problematic in the case of a course, of course. And neutral values, values that don't affect one another, have a zero covariance. So things that are randomly varying with respect to each other. We can construct a covariance matrix by multiplying A by A transpose, where we first of all mean center, that is, we subtract the average of each row from every element of the row. We can do this without, we can calculate this without doing mean centering, but it doesn't mean quite the same thing if we don't center everything at zero. And depending on whether we're interested in a so-called true covariance, or population covariance, or a sample covariance, we often, for the latter, divide by the number of entries minus 1. This converts us to a sample covariance. This is just some definitions. Right? This covariance matrix describes how all of the different possible rows of a matrix are related to one another. You might imagine that we don't only have homework exams and quizzes. We have 11 homeworks, 11 quizzes, 4 exams. That's a 26 row matrix. And we can look at the covariances between all of those, the correlation between all of those. How does performance on homework 1 affect performance on homework 2? Are they related? Are they correlated or not? Is there a correlation between how students did early in the semester on quiz 1 and quiz 2 with how they did later in the semester on, say, quiz 10, and this sort of thing, right? But there's a lot of data in there. 26 by 26, that would give a 26 squared, more than 500 entries, pairwise entries. There's a lot of data in there. How do we wrap our head around all of that data? Well, we can take advantage of this by using the singular value decomposition. Let's think about how we might do that. First of all, introduce an idea. Right? If we take a look at this matrix here, this covariance matrix, it will be symmetric. It's symmetric because it's a product of AA transpose, and we know that it's always a symmetric matrix. That means it has an eigenvalue decomposition. And the sum of the eigenvalues of that covariance matrix gives us what we might call the total variance. Now, we also note that this AA transpose, the eigenvalues of AA transpose, this was what we used to find singular values. Remember, how did we find the singular values? We computed the eigenvalues of AA transpose or of A transpose A. Those will actually give us the same singular values. And since the covariance matrix involves this same product used to derive the singular values, we can equally write this total variance as a sum of the singular values squared divided by the number of samples overall based on this scaling factor. Now, why is this helpful? Well, we've just discussed how we can take approximations of matrices by truncating a sum of this. Remember, these are always in order, with sigma 1 greater than sigma 2 greater than sigma 3, and so on. So the early terms in this sum will dominate. They will dominate even more because we are taking them squared. And so we can think about taking a truncation with the first k terms will explain most of the variance in the data. Right? And actually, because of the ordering of these terms, the first k singular values have to be the k terms that describe more than any other possible set of k terms. This looks just like a low-rank approximation to k. Right? If we take this low-rank approximation to A, we start with our data matrix A, we compute the singular value decomposition, we take a low-rank approximation to that, the variance, the total variance in this approximate matrix is given by the sum of those eigenvalues, which is approximation. These are the approximation to the total variance. But added on to this, we also have singular vectors. The singular vectors U tell us the directions where most of this variation happens. these are what we call the principal components. They are vectors that let us describe reconstruct the matrix as completely as possible with minimum amount of, with the smallest number of components. Okay, so we've discussed two uses of the SVD so far: low rank approximations and the principal component analysis. I want to now introduce one last application, application of a pseudo-inverse to the, of the SVD to pseudo-inverses. Again, let's start with our full decomposition. A equals U sigma V transpose, broken with V and U broken down into a row space and column space piece, and then a null space and left null space piece. If A is square and non-singular, that means that this sigma has to be square, has to be M by M, and it has to be full rank, which means sigma hat is M by M, which means these zero pieces actually aren't there. Sigma is actually just our diagonal matrix with all non-zero eigenvalues, or singular values. That means it has a well-defined inverse. A well-defined inverse taking the reciprocal of all of those. So, non-singular A, we can propagate the inverse through the singular value product, V transpose inverse, sigma inverse, U inverse, remembering to reverse the order, and remembering that U and V are orthogonal matrices. So U transpose equals U inverse, V transpose equals V inverse. That means that V transpose inverse is just V transpose transpose, which is just V, and U inverse is just U transpose. If A is square and non-singular, we can compute its inverse simply by taking this V inverse of sigma U transpose, much like we could use for eigenvalue decomposition for non-singular matrices. However, we can extend this idea to cases where A is either non-square or is singular. Right? Think about this same apologies, full SVD, and replace in our definition of the inverse a new kind of pseudo-inverse of sigma. Sigma in this case has zero entries. This is a R by R matrix, and so if we think about the size of these zero blocks, one of them is M minus R, one of them is N minus R. If either we're dealing with a square matrix, a non-square matrix, then one of these at least has to be have zeros. If we have an R left them both M and N, then all three of these zero matrices will be present. And so what we're going to do is we're going to define a sigma plus, a pseudo-inverse for sigma, that takes only the reciprocal of the place that we can. So we take the inverse of this non-singular rank R matrix and plug that in to a matrix with appropriately sized blocks here. Although it might look like these are the same sort of size, they aren't. Sigma hat will always be N times M, where sigma was M by n. Just as the transpose changes the size of the matrix, that flips the order of the sizes, the pseudo-inverse that we discussed in the context of projections flips the dimensions, so does this pseudo-inverse here. Right? When we have this m by n matrix sigma plus, we then define a pseudo-inverse, A plus, as V sigma plus U transpose. Right? And by the same logic as we discussed before, what this really is can be written as VR, only the row space piece, multiplied by the inverse of sigma hat, multiplied by UC transpose, only the column space piece. Right now, this is a definition, and you can see this n by m has to be sized this for this to work out. V is n by n, sigma plus is n by m, U transpose is m by m. Inner dimensions match and cancel out. We're left with n by m for our A plus, the swapped dimensions of our original A. Okay, this is a definition. What properties does this pseudo-inverse have? Well, A plus, the product, almost gives us the identity matrix. Now, what do we mean by that? Let's plug in our expression for A, U sigma V transpose, and our expression for A plus, V sigma plus U. V transpose V equals the identity matrix, so it disappears. And we're left with U sigma sigma plus U transpose. Now, what does sigma sigma plus look like? Sigma sigma plus, this is an m by n multiplied by an n by m. This is going to give us an m by m matrix. But the upper block will be sigma times sigma inverse. That's the identity matrix. The R by R identity matrix, where R is the rank. And then we'll have zeros as necessary to give us the right size M. And so this matrix in here looks almost like the identity matrix. It has ones up to the first rank, and then it has zeros. Right? So it kind of looks like an identity matrix, but where some of the bottom has been zeroed out. If sigma sigma plus was the full identity matrix, then we would take it away, and if we crossed out that piece, we'd be left with UU transpose, and UU transpose is the identity matrix. So we have something that is close to the identity matrix stuck in the middle of a product that would give us the identity matrix if the matrix in the middle was the identity. Right? It's not quite as simple as propagating out these zeros. We don't get a block matrix in this product, but we can see that that there's an argument to be made that this product is quite similar to an identity matrix. Right? Now, what does it actually look like? We can take this in another approach. A times A transpose should be U times sigma sigma plus U transpose. Let's plug this in. U can be described as UC plus and then ULN, the column space piece, the left null space piece, multiplied by this block matrix with an identity block and all other zeros, multiplied by the transpose of this same vector. IR times UC transpose gives us just UC transpose plus 0. So that leaves us with IR. This first product leaves us with IR UC transpose, and then zeros. Multiplying UC by this gives us UC times IR UC, that I can disappear. And so this gives us UC times UC transpose plus 0. Let's think about this. This A times A plus gives us a product of UC times UC transpose. What does this look like? This is a column space of basis for the column space of A multiplied by the transpose of this. This looks just like a projection matrix. P equals AA plus is a projection matrix. What is a projection matrix onto? It's onto the column space of A. When we have full row rank, then this will actually give us the identity matrix, and we can say that A plus is a right inverse. But for any case, AA plus is a projection matrix onto the column space. We can do exactly the same analysis of the product A plus A. This gives us V sigma plus sigma V transpose. Sigma plus sigma, by exactly the same logic, also gives us a matrix with a IR, an R by R identity block, and then zeros, but it's in an N by N matrix instead of M by M. VV transpose would give us IN if this middle product was the identity. It's not quite the identity, it's only close to it, and so we again have something that's almost the identity, but not quite. Again, plugging in V transpose, V into this product here, V row space component, V null space component. The IR picks out only the VR piece and gives us a 0 in the other part here. And then when we multiply VR times VR transpose plus 0 gives us with only this product. This product, A plus A, is also a projection matrix, but it's a projection matrix onto the row space of A. So we see that these products, A plus and AA plus, are both close to the identity, and they are both projection matrices onto the column space or the row space accordingly. Now, how can this be used? It can be used because the projection matrix comes into play in finding least squares solutions. Right? This UC times UC transpose, or A times A plus, is the projection matrix onto the column space. The way we get a best least squares solution to an inconsistent system is by using the projection. We solve AX equals the projection of the column space onto B, or P times B, where P is AA plus. Right? And this gives us AX equals A times A plus B, where A plus is defined by this pseudo-inverse. Now, I want to be careful here. We cannot simply cross out these A's. What does it require for us to cross out these A's? It would require that there's something that we could multiply A by to give the identity matrix. Right? We could do this if it was non-singular, but or even if it was simply full row rank, but we can't do this when it's less than row rank. What we can, however, do is substitute in the singular value decomposition into these pieces. A becomes UC sigma hat V R transpose. AA plus is the same as UCU transpose. So let's substitute here. Now we can do some substitutions. I can multiply U transpose C times UC. This will give us an identity because we're taking the rows of UC multiplied by the columns of UC, and these are an orthonormal basis. So this gives us the identity. Multiply both sides UC by UC transpose makes these two pieces disappear. Sigma hat is a rank R by R matrix. It is non-singular. We can invert it, so we multiply both sides by sigma inverse. That gives us VR transpose X equals sigma hat inverse UC transpose times B. And then we can multiply sorry, this is on the wrong side here. I want to be careful about what I'm doing here. Sorry, there's a slight issue here because I actually do not believe that we are allowed to do this last piece. VR transpose does not, remember, exactly equal the identity matrix. It equals this because instead this actually equals A plus A. And so let's be a little bit careful here. This last piece should not have been reduced down into exactly this term here. I'm going to revisit this and expand correct this language here on a post in Piazza. I apologize for this confusion here. What in the end we get is an answer, however, where we have a possible solution given by x equals a plus times b, the pseudo-inverse, just as we've seen before. Remember, for a non-singular case, we had x equals a inverse b. For a full column rank matrix A, we could do A equals A plus B, where A plus was defined by this A transpose A inverse A transpose. This, we have a different definition for a pseudo-inverse, but the same thing, a rule applies. This gives us a solution to the least squares solution, and it so happens that this solution actually gives us an answer that is in the row space of A. This pseudo-inverse gives us an answer in a least squares sense to AX equals B. That is, it finds an answer to AX equals the projection of B onto the column space of A, and it gives specifically the solution that is in the row space of A. Right? What can we do with that? From that, we can find a general solution. The general solution is given by adding solutions from the null space to that vector. And because the row space and the null space are orthogonal, we can think about the vector x as being made up of so we have a vector x a row space vector and a null space vector, and these are at right angles. That means we form a right triangle. The length of x is the length of x squared is the length of r squared plus the length of n squared. We have this relationship here. What does that mean? It means that any vector that has a non-zero null space component will be bigger than the length of the vector that has only this solution here. The length of this is always greater than, if we add a bit of the null space, it creates a vector that is longer in a Euclidean sense than this starting solution. This pseudo-inverse, if we start with AX equals B, it gives us the shortest possible solution to the system AX equals P, where P is the right-hand side that is the shortest possible distance from B. And kind of gives us this that we can see the singular value decomposition, the pseudo-inverse, gives us a way to give a precise answer to any AX equals B. It solves the least squares problem if B is not in the null space, not in the column space. When there's many solutions, it gives us the particular solution that is in the row space. We can always get a general solution by adding the null space back into it. All right. I want to wrap up with just kind of describing how the SVD relates to kind of this big picture of the column space and the row space and left and right null spaces. We start with an M by N matrix. A, it has a row space and a null space that together are orthogonal complements and make up Rn. And V is a complete orthonormal basis for this space, separated into the two parts. The column space and the left null space together describe Rm, and U is a complete orthonormal basis broken down into column space and left null space components. The singular value decomposition, U sigma V transpose, can be condensed down into a UC, only the column space piece, only the row space piece, with this sigma hat portion of sigma. And what that means is that we can kind of write a relationship that connects the basis vectors for the row space. I'm sorry, this shouldn't be a transpose here. Let me correct this. Here, A times VR equals UC sigma. The basis vectors from this row space, some VR, can be directly related to vectors UC by a scaling factor sigma. Right? And this is a reversible mapping with what we call a one-to-one mapping. In many ways, the singular value decomposition puts together all of these ideas: row space, null space, column space, left null space, orthogonality of the spaces, orthogonal bases, and through the pseudo-inverse, solutions when there's an exact solution, least squares solutions when there is not, particular solutions to the row from the row space when there are many solutions. All right. That has been a description in qualitative and conceptual terms of how we use the singular value decomposition. One final video will go through some examples of actually using the SVD in practice. Thank you, and goodbye.